Okay, so we'll start now. Today we'll take up eighth experiment, which is steady state heat transfer in a cylinder. So here the question is a hollow cylinder of inner radius 20 mm and outer radius 60 mm with thermal conductivity of 200 watt per meter degree centigrade, and the inner surface of the cylinder is maintained at a temperature of 100 degrees centigrade, and the outer surface heat is dissipated by convection, where the convection temperature is or we can say ambient temperature is 20 degrees centigrade, and corresponding convective heat transfer coefficient is 80 watt per meter square degree centigrade. Then as well determine the temperature distribution in the cylinder and the amount of heat transfer from the cylinder to the surroundings or maybe the atmosphere. So this is the question. So this is the title itself indicates that it is a steady state heat transfer problem. That means there is no time factor is involved in this. With respect to time, it is the temperature distribution is constant. So that means it is not going to vary. So since it is a steady state heat transfer problem, we required only thermal conductivity. Of course, since he has given a convective boundary condition, so we required that bulk temperature and heat transfer coefficient also. So here the problem is again it is a cylinder like what we discussed in the previous problem. That is also cylinder, but there it is subjected to internal pressure. But now here it is subjected to some thermal loads here. Earlier one it is a mechanical load, now it is a thermal load. Irrespective of whether the load is thermal or mechanical, like what we discussed in the previous class, if the given problem is satisfying the three conditions, then we can model the problem as an axisymmetric problem. Those three conditions are there should be a geometric symmetry about the axis, and there should be a material symmetry about the axis, and also there should be the loading also should be symmetric about the axis. So here all the three are satisfied even in this problem also. Even though you have a thermal loads here, those conditions are satisfied for this problem also. So therefore what we do is here also we'll use the axisymmetric approach to solve this problem. So only thing is earlier so far whatever we discussed, those 7 problems, they are related to the structural mechanics problems. Now this problem is related to the heat transfer. So that means the module is different now. Earlier module it is a structural module. Now we are entering into a thermal module. So in this problem now whatever element you need to select now for this analysis, your element should be capable of taking these thermal loads. So that means whatever element you selected in case of structural elements, those are not suitable here because your physics of the problem is changed now. Earlier you don't have, you are considering about only the displacement, strains and stresses. Now we have to deal with the temperature distributions, amount of heat transfer, that means heat fluxes, and also heat generation. If there is heat generation cases there, you need to discuss, you need to deal with those things. So that means here in this particular problem, the field variable now it is a temperature. Earlier problems, the field variable is displacement. So from the displacement, we determine the derived quantities like strain and stresses values. Here, your field variable is temperature. From the temperature, you can find out the remaining derived quantities. That is amount of heat transfer. That is nothing but heat flux. As per your Fourier law of heat conduction, you can easily calculate heat flux is nothing but K into dt by dx. That means you require dt by dx is nothing but the temperature gradient. If you are able to calculate the temperature gradient, means how the temperature is distributed within the element, so you can calculate the amount of heat transfer also. So that means what you have to do is you need to find out what are the temperature gradients. So in order to find out the temperature gradients, our aim of the experiment is also same. We need to determine the temperature distribution in the cylinder. First question is we need to determine what is the temperature distribution, and then from the temperature distribution we can calculate how much amount of heat is transferred from the cylinder to the surroundings also. So for that to prepare the FE model, what we do is, so again here also he has not given the length of the cylinder. He has given only the inner radius and outer radius. So then thermal conductivity and the boundary conditions, that is inner surface is at 100 degrees centigrade and outer surface is subjected to convection. So he has not given. So if you look at the diagram also here, it is something like a section here in the top and bottom. That means you can have any length of the cylinder. You can have any length of the cylinder. So the temperature distribution is independent of the length of the cylinder. That means I can take any length. So it is independent of length. So I can take any length. So I can model. So therefore, again, what we'll do is we'll take the approximate whatever length we want. We can take the length. So based on that, we can model our FE model. So for that, what we require is like in the previous case, what you need to do is you have to consider only the revolving section. So for the revolving section, what you require is you require what is the inner radius, what is the outer radius, and what is the length or height of the cylinder. So inner radius is given to us 20 mm, outer radius is also given to us 60 mm. Then what is the length of the cylinder? So we'll take as per our convenience, whatever you want, you can take length. So whether it is 1 meter or 0.1 meter or any other value, you can take it. So for our problem purpose, I will select the length as 0.1 meters. Okay, so that means I can create the revolving section now. Once I create the revolving section, then I'll select the element which is suitable for this analysis is plane 77. So earlier you have plane 183 for the structural mechanics problems. Now you have to select plane 77 for this thermal problems. So again, you need to select this plane 77 element. So since like I already mentioned, in case of thermal problems, your field variable is temperature. Since the temperature is a scalar quantity, you don't have any direction. That means you don't have temperature in x direction, temperature in y direction, temperature in z direction like that. Because temperature is a scalar. So you will specify only temperature. You won't say it won't have any direction. So therefore here, what you have to do is here our plane 77 element, what we are selecting here, which consists of 8 nodes. So each node consists of only 1 degree of freedom, that is only temperature. So whereas in case of structural mechanics, you selected same 8 node element, but there for each node there are 2 degrees of freedom. Now here only 1 degree of freedom, that is only temperature. So after that, what we need to do is we need to select the axisymmetric behavior, and then we need to convert the geometry into FE model just by choosing appropriate element size. After that, you need to apply these conditions. So at the inner surface, you have a temperature, and at the outer surface, you have a convection, heat transfer through a convection. So that's it. If I do that, I can solve this. Then I'll get the solution. Once you get the solution, from that, what you have to do is, okay, this is the approximate FE model. So it need not be like this. You can choose any length. So here, this is the FE model. What I'm showing here is length of 0.1 meters. Okay, so you can see the boundary conditions also here. We have something yellow color symbols, triangle symbols are there. These are nothing but your temperature. So I applied the temperature boundary condition at the inner surface, and this is the outer surface. You can see the red line here. This red line indicates that so it is going to be the convection boundary condition. So that means at this surface it is subjected to convection. We need to apply that also. And also, since we are choosing the length of the cylinder randomly, so then on the top of this and on the bottom of this, you need to substitute a insulation boundary condition. Insulation boundary condition means the amount of heat flux crossing this boundary is going to be 0. Insulation means the amount of heat flux crossing this boundary as well as this boundary, it is 0. Why it is 0? Like I already said, so your temperature distribution is independent of length. If you take any length, it is not going to change. That means across this length, that means if I move in the y direction, so the temperature remains constant. So temperature remains constant means what happened to your temperature gradient dt by dx? dt by dx will become 0. Since your heat flux Q is nothing but k minus k into dt by dx. Since your dt by dx is 0, your heat flux is also 0. So heat flux is 0, I will call it as a insulation boundary condition. So therefore, I need to assign insulation boundary condition for this edge as well as for the bottom edge, because I am using the symmetry boundary condition here. So once I done that, so that's it. I need to go for the solution. Once I solve this, what I need to do is I need to take the temperatures like this. So across the radius, that means across the thickness. So this is the inner radius and this is the outer radius. So to in order to plot or in order to find the temperature distribution across this thickness or across the cylinder, what you need to do is at a specified radius, you need to identify what is the temperature at each radius. Then you need to note it down those values. So that's what we need to do here. So initial radius, inner radius, it is 20 mm. At 20 mm, what is the temperature? Then we'll go on increment with the increment of 2 mm or 5 mm. Let us say it is 4 mm. If you take 4 mm like that, so you can go for with an increment of 2 mm. So that means first 20 mm radius, 22 mm radius, 24 like that. I'll go up to 60 mm radius. I need to note down what are the ANSYS results. Then you need to compare this solution with the analytical solution also. So from that, what you have to do is I have given an analytical formula also here. So first what you have to do is to verify this to temperature distribution. First we have to compute the Q value. First we'll verify the Q. Q for that we have to use the second formula. So in this formula, everything is given to us. T is given, that is T is nothing but a T1 here, inner surface. T1 minus T infinity divided by 1 by 2.5 KL into natural logarithm of R by R2 by R1 plus 1 by 2.5 HR L2. L R2. So here everything is known. In this T is nothing but the inner surface temperature, which is 100. T infinity is given it as 20 in the problem. K is the thermal conductivity. L is the length of the cylinder, what you have considered. R2 is outer radius and R1 is inner radius. So H is the convective heat transfer coefficient. So everything is known to here. So from this, what you can do is first I will compute the Q value. If you substitute those values here, whatever values he has given, if I take length is 0.1 meter, this Q is come out as 235 watts. Now, once I calculate the Q value, then I'll use the second portion of the problem to compute what is the T2. If need not be T2, wherever I want, I can calculate the temperature. That means, suppose if I want to calculate the temperature at outer radius, so here I have to substitute T2 value. So here I have to substitute R2. Suppose if I want to find out the temperature at any other radius, let us say at 30 mm radius. So here I have to take this T instead of T2, I have to substitute this one by T at radius R is equal to 30. Here I have to substitute instead of R2, I have to substitute radius at 30 mm. That is R is equal to R2 is equal to 30. I need to substitute like that. If I use this formula, because we already calculated Q using this formula, so now I can compute the temperature at any point. So I can fill this table. And for the analytical solution, then I can compute the percentage of error also for this. And of course, from the science solution, we got all these results. So now you need to compare and you need to find out the error. Then after doing that, you need to draw the graph. So what I will do is I will ask you to do it manually. So you need to draw a graph paper because nobody is following the class or nobody taking it is serious. So just you are for the sake of something like that, you are attending and you are leaving. You are not. What I observed is you are not learning anything. So what you have to do is you need to draw the graph manually. So whether you have a software with you or not, maybe at the end of the semester you need to produce the graph. So you cannot say that I don't have any software with me to practice. You come to the college and you have to practice it. So after some time, maybe college may be open. So at that time you have to practice during some practice hours. So then at that time, you need to draw the graph manually only. If I show, if you want, you can draw it in the software also. But my intention is, you want to draw this graph manually, not using the software. So for that, what you require is, so here you have already the result. What you are doing here is, in the table you have a result. At a given radius, you have a solution, temperature. So then, x-axis you need to take the radius as x-axis and y-axis you need to take the temperature and then you need to plot the curve. So how you are getting the curve, that is going to be your variation in the form of a graph. Instead of table, you are showing it as in the form of a graph. That's it. After that, so once you compare the solution with the analytical solution, then you can write some comments on your results. What about the accuracy of your results with respect to your analytical solution? Then, if they are not accurate enough, what are the ways of improving the solution accuracy? If they are okay, then what are the reasons for that? Like that, you can write the discussion. So before going into that, I want to remind one more thing here is in the problem. So if you look at the K value and H value, they are in meters. See, K is given as 200 watt per meter degree centigrade and H is given as 80 watt per meter square degree centigrade. But our radiuses are given in mm. So don't take two different units for the same parameter. That means for length meter, wherever you have, whether you have to follow mm or we need to follow meters. So that means here, either I can convert this K or W in terms of for mm square. Here this one is for mm or this one is for mm square. Or I need to convert these radii into meters. So either way you can do that. So what I prefer here is, since you are converting these two things into mm, what I'll do is I'll try to convert the radii into meters because that is the easiest way of doing it. If you want, you can convert these things so into mm also. But what I prefer here is I'll convert the radius into meters. Okay, right. So with this brief introduction, I'll take you to the software and I'll show you how to solve this problem. So first I'll change the job name to the steady state analysis of a cylinder. A steady state thermal analysis. Okay. Whatever is given there, that comes out here. So I'll save this. Okay, now see, now we'll use this preference option. So if I click on this preference, see, you can see, like I said, you have two different modules, structural and thermal. Now I'll pick thermal. So far, whatever you problems you solved, there comes under structural category. Now we are solving thermal category problem. So I'll select thermal here. So the advantage of doing this is, so now if I select thermal, the software filtered out all the unnecessary things which are not related to thermal analysis. So now it will retain the features which are related to only thermal analysis. That means it won't show you the features of structural analysis. So that is the advantage. But it won't modify your solution accuracy or anything here. So just only to filter out the things which are not related to thermal analysis, we use this preference option. Okay, then first I'll add that element type, add, then click add here. So here I have to select again solid 8 node 77, you need to select, click OK. So it added here. So then you need to set that axisymmetric behavior here. So you need to go for element behavior under key point option 3, you need to select axisymmetric, click OK. Then I need to define the material properties. That too we need to define only the thermal conductivity. So here, see, now only thermal is listing here. Earlier, if you can see, earlier I have a structural, now it is showing only thermal because I used preferences as a thermal. It is listing only the material properties related to the thermal analysis. If I want to select this preferences option, let us say, I'll go back. Okay. So for that, I need to close this. See here, if I uncheck this, now click OK. Then if I click that material models now, you can see all the things are listed here. Only thing is, if you select that preferential, so this structural, all these electromagnetic, acoustic, fluid, piezoelectric, all these things will be filtered out. That is the only advantage. Otherwise, other than that, there is nothing great about this option. So, okay. So anyway, I need to select the thermal properties here. I need to select thermal. So I need to define the conductivity. So since we are taking it as isotropic, thermal conductivity Kxx is nothing but 200 watt per meter degree centigrade. I need to enter here 200. So if you want, you can define temperature dependent also here, but we are assuming here T1, so you can add temperature dependent thermal conductivity also. but we are treating the thermal conductivity is constant, so I don't bother about the temperature variation for the conductivity. That's it. So once I done that, then what I'll do is I'll go for the geometry creation. So for that we need to create only the rectangle or revolving section. So for that I'll go for areas, rectangle. Then I'll use this bidimensions option. Now, as we discussed in the earlier problem, x1 and x2 corresponding to the inner and outer radii of the cylinder. So inner radius is given as 20 mm. So I want to convert that one in meters. So I need to write it as 20 e minus 3, and outer radius is 60 mm, which is equal to 60 e minus 3 meters. Then I'll take the length of the cylinder, like I mentioned, I'll take it as 0.1 meter as my length of the cylinder. Click OK. Right? So your revolving section, this is the axis of revolution, Y is the axis of revolution. So this is going to be your revolving section. So once you created this, then what you have to do is you need to convert this one into geometry into FE model. For that, we need to use mesh tool. So go for meshing and mesh tool. So in this, before going into the meshing, first I want to specify how many number of element divisions are required. So like in our result table here, so if you want to note down for every 2 mm radius, if you want to have a here, like in the table, what I shown to you here. So whatever you want here, radius. So first I will start with the inner radius, and I need to end with the outer radius. So anyway, that is you are going to get for inner radius, for outer radius, definitely you will get the results. In between, at what distance or for at what increment of radius you want to get the result. Based on that, you need to divide your element. You need to divide your element edge length. So for that, what you have to do here is, okay, suppose if I want to have for every 2 mm thickness, for every 2 mm thickness, if I want to have a temperature result, so then what I need to do is I need to consider edge length of each element is going to be 2 mm. That means, so I can define into either two ways. So this total distance, it is 40 mm, so that is 40 e minus 3. Accordingly, I can do that, or else directly by specifying the 2 mm means, so I need to divide this one into 20 divisions. If I do that, again I will get the same thing. So that means I can specify either edge length or I can specify the number of divisions. So here, instead of specifying the edge length, I can specify the number of divisions also, or else I can specify the edge length also. That's why here you can see the two options are available to you. Either you can specify the edge length or you can specify the number of divisions. So what I'll do is I'll specify the edge length, let us say 2e minus 3. That is nothing but for every 2 mm, I want I want to know the temperature distribution. So after doing that, you need to mesh. Sometimes it will do it quickly. Maybe today I don't know why there is some problem with my system. It is somewhat lagging today. Anyway, so this is going to be our FE mesh. If you look at this FE mesh and what I have given in our document, it is somewhat different here. You can see that also. In the vertical direction, you can see that here the edge length is different. In horizontal direction, okay, it is okay. But in the vertical direction, you can see here you have a less number of elements when compared to this. So you can do like that also, because like we already discussed, in the vertical direction, it is independent of temperature is independent of this direction, that is length. So you can have different mesh sizes in horizontal and vertical direction also. Anyway, so here we are given uniform. So okay, even if same solution also, no problem. Okay, right. So what we did is we meshed this. So once after meshing this one, you need to apply the loads and boundary conditions. For that, you need to define, first you need to define those thermal loads, that is at the inner radius or inner surface is nothing but inner radius, you need to apply the temperature. So for that, I need to go for apply thermal temperature, then I'll use lines option. So because this line, this inner line, will represent the inner surface. I'll select temperature and here I'll enter the value as whatever value is given, that is 100 degrees centigrade. See now it is placing some triangles here. You can see that yellow color triangles, whatever I shown you in the FE model. Then what you have to do is you need to apply the convection boundary condition here. So that is nothing but you have a convection boundary condition also there. You click on this convection, then click on lines. Then you need to select the outer radius. Click OK. Then it will ask for what is the film coefficient. Film coefficient is nothing but your convection heat transfer coefficient, which is 80. And then it is asking for the bulk temperature, that is the ambient temperature, 20 here. Okay. Okay, you can see now a arrow is placed like this, saying that you applied a convection here. So then, after that, we need to apply the insulation boundary conditions also. So that is, heat flux is 0. So you need to go for heat flux on lines. So you need to select this top line and this bottom line. Click OK. And since it is insulated condition, I need to enter it as a 0. Even if you leave it blank, it will take it as 0. So that is also applied. So that's it. So you need to, we completed everything. So once you're done with it,
Hello, sir.
Hello? 336? సార్ కలాం గారు ఉన్నారా?
వినిపిస్తుంది సార్.
అడుగా మధ్యలో డిస్కనెక్ట్ అయింది కదా, ఎప్పుడు డిస్కనెక్ట్ అయింది?
ఒక 5 to 10 minutes అవుతుంది సార్. 5 minutes దాటింది.
సొల్యూషన్ దగ్గరగా వెళ్ళారా?
ఆ సొల్యూషన్ సాల్వ్ చేసే దగ్గరికి వెళ్ళేటప్పుడు డిస్కనెక్ట్ అయింది సార్.
అవునా? మరి నాకు ఎవరు మెసేజ్ పెట్టలేదు, ఏ లేదు, నేను ఆవతని చెప్పుకుంటే వెళ్ళిపోయా. ఏ ఇంటర్నెట్ కనెక్షన్ ఏదో బ్రాడ్బ్యాండ్ కనెక్షన్ ఏదో నెట్వర్క్ ప్రాబ్లం ఏదో వచ్చి డిస్కనెక్ట్ అయింది. ఓకే, ఎనీవే, సో నేను క్లోజ్ చేయలేదులే. ఓకే, సో ఐ విల్ షో ఇట్ టు దిస్. సో దట్ మీన్స్ యు ఆర్ గాన్ అప్ టు సొల్యూషన్, రైట్? ఓకే, ఓకే, ఐ నీడ్ టు గో ఫర్ ప్రెజెంటేషన్ మోడ్. Okay, so once you solve that, then what you have to do is we need to see the results. So for results, I think now you are able to see my screen, right?
Yes, sir.
Okay. Anyway, so okay, so it is solved. Then what we do is, first what we'll do is we'll plot the result, then we'll list the results. So before going to the plot, first whatever we want to do here, whatever I given in the document, we need to compute that K value, Q value, not sorry, K value. It is Q, that is amount of E transfer. We need to compute that. So like I already mentioned, the Q values comes out as, if I use the second part in that analytical solution, I'll get Q value. So the Q value is 235 watts, what we are going to get. So let it open. So meantime, I'll take you to the software and I'll show you how we'll get that value. So you go for general post processor, then in that you need to go for list results, then you need to select the reaction solution, because heat transfer will comes under reaction heat flow. So then if you click on the reaction solution, you can see here heat flow is there. Click OK here. Okay, maybe okay, I'll do one thing. I'll select everything now, because after that I done something. So now I'll go for this. See now, for each node how much you will get here, for each node how much is from through each node how much it is transferred to the surroundings from the cylinder. So like this, you have so many nodes. So if you add up all this heat, then only you'll get the total amount of heat transfer to the surrounding. So that is also given in the software here. You can see the total. The sum of all these values is going to be 235.08. So that means whatever our analytical solution will give you, here also you are getting the same thing. So that means they are exactly matching. So now if I open the document, I get the same value. So anyway, meantime it will okay. It is not now open. some time. Okay, so anyway, so we got it as 235. In that analytical formula, through that analytical formula also we'll get the same value. So once you've done that, next what I need to do is I will go for the plot result also to see how the temperature distribution is going to, or how the temperature distribution will be. So for that I need to go for plot results, nodal solution and nodal temperature. I need to select. So here already I use this symmetric option here. So like what we did in case of previous problem, style symmetric options here I gone for. So if I take no symmetry expansion, then I'll get this is going to be the original graph contour plot what we are going to get for temperature variation. See, you can see that at outer radius, this blue color indicates the outer radius temperature, and red color indicates the inner radius temperature. You can see that across the length, you can see from the top to bottom, from the bottom to top. So you can see the contour band is same. That means no variation across the length of the cylinder for the temperature. That's what we assume. That is reflecting here also. That means it's okay. So that means your temperature distribution is now independent of your length. But amount of heat transfer is function of length. If you don't use length there, you won't get the correct value for the validation. See now red indicates 100 means at the inner radius it is 100. That's what we applied. At the outer radius, so it comes out as 97.95. So this also you can verify with the your analytical solution what I have given in that document here. I given two parts in this solution, that is analytical formula. First part will use to second part, this part of the formula will use to compute the Q value. So in this formula we know everything. So K is known, L we are taken as 0.1 meter, R2 outer radius, R1 inner radius, R2 outer radius, H is the thermal heat transfer coefficient, convective heat transfer coefficient. So everything is given. T is the inner surface temperature, that is 100, T infinity is 20. Everything is known here. If you substitute those values, you will get Q. That is nothing but 235 only you are going to get. So that is the first validation. Second validation is now if I want to calculate the T2, that T2 is the temperature at the outer radius. I have to use this formula. Now I know the Q value. So I know everything except T2. So I can use this formula to compute the T2 value. So if you compute that, it will comes out as around whatever we got in the software. So the same value you are going to get here. That means exactly your analytical formula result and analysis results will coincide with each other. So then similarly, we have a table with these results. See, you can see radius, and you need to write the result for every successive radius of 2 mm. So that means inner radius is 20 mm, then 22 mm, 24 mm, 26 mm, like that up to 60 mm. You need to get the temperature value. So to find that value, again what we do is we need to use this formula only. So in this formula here, instead of T2, wherever you want to find the temperature, here in place of R2, you need to substitute its corresponding radius. That is, Q remains same, that is 235 only. Only thing is this T2 and R2 will change wherever you want. Suppose I want to calculate at a radius of 30 mm. So I need to substitute R30. So now if I solve this equation, from that I'll get whatever value for this T2, that is going to be the temperature at R is equal to 30. So like that, I can calculate the temperature for all the nodes, for all the radiuses. Okay, so that is what about the analytical solution. Now if I come to the software solution, so what we need to do here is, okay, I'll open the software. So in the software, just now we plotted it. So but from the plot, I don't know. From this plot, I don't know at what radius what is the temperature. Of course, only exactly I can know that this is the inner radius and this is the outer radius. But I don't know. This 98.8583 is there. At what radius this is the temperature? I don't know from the plot. So therefore, what you have to do is you need to go for. In that case, you need to go for the list results. Okay, so it is taking some time. Let it be. Okay, it is hanged out. Yes. Okay, so what I'll do is, anyway, I saved this, so I'll close and open it again so that it will work. Hello. Are you able to hear me?
Sir.
Okay, what you do is, now I'm closing it. Maybe there is some problem with the software update. I think it is updating, Windows is updating. That's why it is taking a lot of time. So what I'll do is, I'll close this class now. Just to join in the next class. We may have a lab class in lab session next now. After completing that lab session, again I'll continue. I'll take some 50, maybe maximum of 15 minutes it will take. So you rejoin again within those at the end of the class. Just you rejoin for the 15 minutes so that we can complete this experiment. So now you leave the class, again rejoin after 15 minutes. At the end of the second class, second lab, that is machine dynamics, again rejoin the class. Okay, then we can finish that one. So now I am closing this class. So you also leave the class.